Welcome to this presentation on machine learning modeling approaches that can be taken to solve traffic recognition problems. This presentation will first explore modeling undertaken for assignment 2 of this course, followed by comparisons to academic and industry standards in the field. With the advent of driverless cars and increased autonomy, there has been a growing need for accurate image recognition models. For driverless cars to become viable, they must be able to identify road signs and interpret their meaning safely. These cars may one day be interconnected, being able to avoid each other using this network. However, until this point is reached, all cars on the road must be able to maintain the current road safety standards, with sign recognition its most basic requirement. This problem was explored during assignment 2 of machine learning, with multiple machine learning models built to try and solve this problem. These techniques will be compared to those used within the academic and commercial worlds. The goal of assignment 2 was to build 2 machine learning models to identify the shape and type of traffic signs found on the road. The initial simpler model aimed to identify different shapes of the signs found, such as round for speed signs and triangles for give way, etc. The second, more complex model aimed to identify the type of signs themselves. This second model is more indicative of what is required for commercial applications such as driverless cars. There were 2 sets of data used for this project. The first was provided for the assignment, this being used for training and validation phases, and the second was sourced by myself for the testing phase to see how the model will perform on unseen data. On the slide, the spread of data across different sign types and shapes can be seen. Multiple techniques were explored as possible options for this project, but neural networks were deemed the best approach for the image-based dataset. Within neural networks, there are a handful of possible techniques to implement these models, with the main 2 explored being multi-layer perception and convolution neural networks. Both model techniques are implemented in a similar manner, with layers of connected nodes leading from an input layer to a final output layer with deciding image classification. The main difference being CNN models can consider more spatial relations with a tensor input and have only sparsely connected nodes. Both implementations had a baseline model built with the best of these parameter tuned to try and achieve the highest accuracy and lowest loss scores for train and validation before final testing was completed. The shape model was built first, so it could be used in conjunction with multiple sign type models. For any given image, to identify the type, it would first pass through the shape model, then pass through that given shapes model for its type model. This allowed for the reduction in classification categories for each model, as building one model for the roughly 35 sign types would become too complex and lead to lower modeling performance. Both the type and shape models performed decently in testing. To be expected, the sign shape model performed above the performance metric of 75%, with final testing showing results of around 85% accuracy. This high performance was expected after EDA showed clear differences between each sign shape and with only 5 shapes to classify. The sign type classifying showed average results of around 65% accuracy. This result shows that the subtle differences between some sign types became harder for the model to classify. These results are a solid first effort, but still well below what will be required in a commercial setting such as driverless cars. Industry and academic techniques will now be examined to see if higher results can be achieved. Traffic sign recognition has become a burgeoning industry with the introduction of driverless car vehicles. In both the academic and commercial spaces, image recognition has become one of the main influences on the development of neural network models. Open source projects are one of the main ways in which better sign recognition models have been developed. One such project is the German traffic sign benchmark run by the Institute of Neuroinformatics at ETH Zurich. Kira-san and his co-workers discussed the best approach taken in this project, with the highest achieving a recognition accuracy of 99.15% across 43 sign classifiers. The approach taken by his team involves the use of a committee of CNN and MLP models. The CNN model is built in a similar fashion to the one used in assignment 2, however the layers are fully connected using 5x5 pixel kernels for each layer. This layer network is shown in the figure to the right. Another alternative to this CNN model also employs fixed localized filters, unlike the learned weighted figures produced in Assignment 2. This CNN model is supplemented by an MLP model that is trained on feature descriptions to offer complementary information for the model. The CNN model is trained on the raw pixels, whilst the MLP model is trained on feature descriptors. This committee of a CNN model and an MLP model shows a much higher accuracy rate can be achieved than that in Assignment 2, something more in line with what is needed for driverless cars. Many implementations of sign recognition models are space and computationally constrained. Moving vehicles do not have the required connectivity to relate each sign back to a central computing unit, and only have the computational capabilities of the car at hand. Zhang and his co-workers explore the options for running lighter networks on resource-poor hardware. These networks are implemented with a teacher and student network, with knowledge distillation transfer from the teacher to the student. This student model showed accuracy results around 99.5%, similar to that of the high-powered network models. To slim down the computing powers needed for the CNN model, the number of fully connected layers was capped at 5, with batch normalization used to prune the redundant channels from the student network. Each layer also only uses 1 by 1 pixel density. This results in a far lower computational needs than the 5 by 5 layers shown in the German benchmark model earlier. The model produced for Assignment 2 had no resource and time constraints, something that would not be practicable for real-world use. The main extension for this assignment is to try and develop a CNN model who could achieve higher accuracy results while still running on computationally constrained equipment, such as driverless cars. To test these model requirements, computational resources with time limits could be included within the performance metrics for testing. Whilst a model accuracy score is simpler to choose, the time and computational power chosen will need to be determined by industry standards. Teraflops can be used for a way to measure CPU power, whereas parallel tasks per minute can be an effective GPU power measure. Whereas time can be determined in milliseconds, with industry standards determining how long human takes to identify traffic signs on the average drive. These metrics can be included in the performance metrics to determine whether the model can perform on restrained computational power and low memory. Thank you.